Hey, welcome to part 2 of Thermochemistry. This is Mr. Ayton, and welcome to Nellen High School. Hopefully you really enjoyed part 1 and you thought it was easy. Part 2 is absolutely even easier. And we're going to get right to it tonight. The first thing we're going to talk about is Hess's law, which is another way to find the enthalpy of the reaction. In part 1, we learned about one way to find the enthalpy of a reaction, and that was when we've been given the heats of formation. Okay? And we're going to sum up all the heats of formation of our products and minus the sum of all the heats of formation of our reactants. But tonight we're going to take a look at another way to find the enthalpy of a reaction. And this is when we've been given a list of reactions. When you've been given a list of reactions, go right to Hess's law. And there's two rules, two options that we can do with each of these reactions. One of them is we can flip the reaction. But if you flip the reaction, you want to make sure you flip the sign of the enthalpy of the reaction, which means you got to flip the positive to a negative or the negative to a positive. The second thing you can do is you can multiply or divide the coefficients. If you multiply or divide the coefficients, though, you have to make sure you multiply or divide the enthalpy of the reaction by the exact same number. And at the end, you're going to make sure you add up all the enthalpies of the reactions to get the final enthalpy of the reaction. Okay? And that is Hess's law. Let me give you an example of what Hess's law is. Take a look at this example. We have 3 reactions. We have a list of reactions. We're going to do Hess's law. We have a first reaction where we're producing carbon dioxide gas. Second reaction where we're producing liquid water. Third reaction where we're producing C2H2, which is ethine, that one with that triple bond in the middle. And it says, based on the information above, what is the delta H for the following reaction? And you can see in the reaction in blue, it's given us the combustion of ethine. So what you want to do is you want to zero in on each reaction. So let me just take a look at the first reaction and take a look at my target in blue of what I want it to look like. And look at the carbon dioxide. The carbon dioxide is one thing that is in both reactions. And in the first reaction, my carbon dioxide has 1 mole. Whereas in my target reaction, what I want it to look like, it has 2 moles. So what do I want to do with the first reaction? Of course, I want to multiply that reaction by 2. And you can take a look. I'm going to multiply. I have 2 carbons now, 2 oxygen gases, and 2 carbon dioxides. And that multiplies my delta H by 2 as well, which becomes negative 787 kilojoules per mole. Let's look at reaction number 2. I'm going to zero in on the water. I have 1 mole of water in the product side. And what do I want? 1 mole of water in my product side. So for reaction number 2, I don't need to do anything. I can keep it exactly the same, which means the delta H stays exactly the same. Let's take a look at my third reaction. The C2H2 is what I'm going to zero in on. And you can see it's in the product side, whereas I want it in the reactant side. So what do I have to do? Flip reaction 3, which means the C2H2 goes to the reactants, whereas the 2 carbons and the 1 hydrogen gas goes to the products. And take a look what happened to my sign. It went from positive 226.8 to negative 226.8. If you take a look, when I add up everything, take a look at what cancels out. My 2 carbons are in my reactants and products. Those cancel out. My hydrogen gases cancel out, reactants and products. And my oxygens become 2.5 or 5 halves. And everything else is perfectly done. So what do I do to my delta H's? I add them all up, and I get negative 1299.6 kilojoules per mole, and that's the heat of my reaction. We're also going to take a look at some stoichiometry tonight. Take a look at this heat. I've given you the heat of this reaction. It's the combustion of methane. And it says if 32 grams of methane was combusted, according to the reaction above, how much heat was given off? Well, if we know we have 32 grams of methane, if we have grams, what can we do immediately? Divide by the molar mass. So if we divide by the molar mass, which is 16 grams per mole, you can see how many moles do we have? 2 moles. Now, since we have 2 moles, take a look. If there's negative 900 kilojoules for every 1 mole of methane, then of course we have at the end, we've given off 1,800 kilojoules of heat. We've released or negative 1,800 kilojoules of heat. Now, I just want to make a note. If we were doing this calculation for water per se, it would be negative 900 kilojoules for every 2 moles of water, because we have 2 moles of water in our reaction. So that is our stoichiometry. The question that you want to do, and you want to finish up for Thermo Part 2, is this. I've given you 3 reactions up top. I've given you 3 heats of the reactions. And I want you to calculate the enthalpy of the reaction based on the information above for the reactions carbon plus 2 hydrogen gases give me methane. And for Part B, it says if 36 grams of carbon was used in the reaction in Part A, how much heat was absorbed or released? Also indicate whether this heat was absorbed or released. So you're going to do Part A and Part B. And when you finish Thermo Part 2, you want to go to MrAyton.com just like in Part 1, and you want to go to the contact page. And when you go to the contact page, you're going to send me an email with your answers. Okay, make sure you write down your work. That way, if it's wrong, I'm gonna have you try it again. If it's right, I will send you an email back letting you know that you are good to go. Tune in to Thermo Part 3 and have a great Christmas break, just like I said. Thanks, guys.